and welcome back to another lecture of Statistics 479 Time Series Analysis. Today we are nearly done with our lectures for this course, and we're going to be talking about estimating the spectral density for the third time, in fact. But don't worry, it's going to be really interesting today. We're going to use parametric methods. So far, whenever we've tried to estimate the spectral density, thus far, we've used the periodogram and smoothed versions of the periodogram. This falls into the category of non-parametric statistics. But as we learned a few lectures ago, if we have an ARMA process, we can just compute the spectral density of that ARMA process exactly. Now, we don't have the actual ARMA process that we want to work with. But what we do have is we have the ability to estimate, to fit an ARMA process to our data, and if we do that, we can just compute the spectral density of the fitted model rather than the spectral density of the data itself. So how do we do all of that? In today's lecture, we're going to be looking a lot at R code, because one thing we haven't done so far is actually try to work with real R code. And it's going to be important because there's lots of different ways to compute the spectral density or to estimate the spectral density in R. And we're going to look at all of these methods and more in the second half of today's lecture. So let's get back to the notes. And welcome back to another lecture of Statistics 479 Time Series Analysis. Today we're going to, be looking at how to estimate the spectral density for the third time. We're going to do a little bit more follow-up in the notes, or a little more, I should say, an extension of what we did before in the notes. And then we're going to look at some R code as to how to actually estimate a spectral density in RStudio, which is going to be, hopefully even more useful than looking at all of these notes. So far, we've looked at a lot of different methods. We looked at estimating, just computing the periodogram via the Fourier transform. We looked at different types of ways to combine our data. We looked at Bartlett's method, where you take little snips of your time series and then average the periodogram over those snips. We've also looked at a lot of other different methods of various ways to band and taper and combine our estimates of the periodogram, that is the intensity of the signal at a given frequency, but averaging over multiple frequencies in order to improve our estimation. And what we got out was a bunch of chi-squared statistics, asymptotically that is, which allow us to do things like hypothesis test and confidence intervals, which are always good times. Now, there's one other method that I want to talk about today, and that's a parametric approach, because so far, everything we've been doing can fall into the category of non-parametric statistics. What we're effectively doing is just trying to estimate the autocovariance, transform that into a periodogram and the spectral density, an estimator for the spectral density. But there's no explicit parametric model assumed. Now what we're going to do is assume a specific parametric model. That is, we're going to pretend that our data is an autoregressive process or an ARMA process, and then figure out how to estimate the spectral density based on that assumption. And it turns out that you can actually get a lot of good results by trying to fit an ARMA process to your data, and then computing the spectral density for that process rather than computing the spectral density for the data itself. So I'm not sure if that's 100% clear, but we're going to jump into the notes and see how this all works together. So let's get into that. All right, so the main topic of today, or this short version of written notes, is going to be not periodic, parametric estimation of the spectral density. But first, I wanted to talk a little bit. First, though, we're going to talk a little bit about that Daniel Kernel again, with two L's. Assuming yes, I believe it's with two L's. So when we go into R, right, the Daniel kernel, this was a way of smoothing out the periodogram when we're trying to estimate the spectral density. So the way I presented it last time was, we'll just keep it in blue as a side note. For a sequence UT, which is real valued, what we can do is we can construct a U1 T, which is going to be a, I guess, 3-point moving average, you could say, in the sense that I'm just going to average 3 adjacent time points together. And again, this is a kernel. It can apply to any sequence of numbers. In our case, we're going to apply it to the the estimated periodogram. And then I also mentioned that there's a modified Daniel. And then, well, the next thing we would do there is we would iterate this to get a U2 and a U3 and so on, which would be smoother looking. And then there was the idea of a modified Daniel kernel, which looked something like UT minus 1 over 4, UT over 2, UT plus 1 over 4. Now, I didn't do this in complete generality. This is how I presented it last time, but I realized that when trying to write up some R code for today's lecture, I realized that actually, yeah, you can generalize this. Well, you can extend this to larger windows, right? You could instead take this first guy and you can, to like really just keep switching colors and be annoying about it, we'll use green now. We could have I guess a kernel of length. I'll use H. I'm a little bit hesitant to because we always used H as a lag, but we can do that. If H is an odd number, we can have UT minus H over 2 plus all the way to UT plus all the way to UT plus H over 2. And we can divide all of these by H. And similarly, what we can do is we could get a modified kernel where the modified kernel is going to, well, it's kind of annoying to write out for general H, I guess. Basically, I'll just hand wave my way past that and say, do as before, but I guess shrink the value at the endpoints. Which is going to look roughly something like UT minus H over 2 divided by, we'll say C1, and then UT minus H over 2 plus 1 divided by C2, UT divided by C2, UT plus H over 2 minus 1 divided by C2, and then we're going to bring C1 back for the final point. I believe this is what's going on in R. We'll look at some examples. Well, actually, we can extract the Daniel kernel from some of the behind-the-scenes functions in R. So what we'll do is we'll actually plot some of these kernel functions out just to get a sense of what they look like. But I believe it's going to do something like this. But you always have to be a little careful because there's so many different ways that you can, I guess, initialize, or you can start one of these things you can code it up in R, and they're all gonna kind of do the same thing, which is they're gonna smooth out the periodogram, and there's no real right answer as to like how big the window should be or how small it should be, if you should modify the ends, if you should iterate this multiple times. Because remember, in the last lecture, we started with U1 here, but we could iterate it to get a U2, which is going to look like a triangle, U3, which will look a little bit more like a, I guess, piecewise quadratic, even though it's going to be extremely discrete. So anyway, that's just a quick little note on Daniel kernel there. Shout out to all the Daniel kernels out there.
And now what I want to do is actually get back to the main topic of today's lecture, or at least the written part of today's lecture, which will be the parametric estimation. So basically, instead of computing the periodogram directly from the data, this is the non-parametric way to do it. We could instead fit an ARMA PQ model and I guess get the periodogram from that. Get the periodogram, well, from our ARMA PQ model. Because if you remember, I think it was 3 lectures ago when we talked about this idea of filtering, and we said, well, we could start with a white noise process. Now we know that's going to have a constant spectral density. Then if we want to get the spectral density for some ARMA process, we can use the characteristic polynomials, the autoregressive polynomial and the moving average polynomial, and we can effectively multiply, use that polynomial, evaluate it at the complex exponential point to figure out what the spectral density for an ARMA process would look like. Now, again, that's all mathematical. We're not basing that on the data. We're saying that if we have a stochastic process that follows an autoregressive moving average, I guess, model, then we can compute what the spectral density should look like exactly based on the coefficients. In practice, nobody just hands us an ARMA process and says, here you go have fun with it. They hand us some data. But we can use that data to estimate phi and theta, and then we can, from there, compute the periodogram, right? So step 1, compute the phi hat and theta hat. And then step 2, compute f hat x, which is going to be our estimate of the periodogram for some value, well, for any value, I guess, omega, in the interval, closed interval, -1/2 to +1/2. Okay. In fact, we can actually do even a little bit better. So instead of fitting an ARMA PQ, we can just fit an ARP process to the data, which is, i.e., estimate, well, I guess choose a P based on, say, AIC or BIC or whatever, and estimate phi hat I. Or I'll just say phi hat for all the different autoregressive parameters phi. All right, so why would we do it that way? Well, for one, that's how it's implemented in R, which is a terrible reason to do it that way. But it's kind of hints that probably somebody smart thought to themselves that we should just worry about the autoregressive piece and not the moving average piece. So if you go into R, which we'll do later in this lecture, you'll see that you can compute the spectrogram based on fitting an AR model to your data. So what that does is it basically uses the AR function to fit an AR model based on P, well, choosing P based on AIC. I think it's AIC or possibly one of the other criterion, but usually it defaults to AIC. Always good to check how every individual coder coded up their algorithm. Regardless, once you calculate those coefficients phi, you can then turn it into an estimate of the spectral density. That is, we can get a periodogram out for that. And it turns out that, in fact, doing this just for the AR function or the AR process is really just as good as trying to do it for the ARMA process. And there's going to be a result that we'll talk about in a minute that will prove and say, okay, if we fit an AR model, it's going to be good enough for estimating the spectral density. Now, personally, I haven't tried to see if fitting, trying to estimate an ARMA model or some more complex model and then using that to compute a spectral density will get you any benefits over just using the AR. So for this course, we're not going to sort of explore that topic, though I think it would be an interesting thing to explore because honestly, it seems like you could try to fit other time series models and then compute a spectral density from it. In this case, the answer that we're going to do is fit an AR model, compute the spectral density. So, well, we're just going to jump down to kind of the answer, which is, so after computing, estimating, let's say phi 1 hat through phi p hat, we get that the estimate of the spectral density f hat x here at some omega is going to just be the estimate of the variance of the white noise process that underlies this, right? Because remember that we always have some white noise process that's behind the scenes. Its variance is going to be sigma squared. We don't know what sigma squared is, but we can estimate it as sigma hat squared from the fitting the parametric model to our data. Then in the denominator, what we're going to have is the squared modulus of the autoregressive polynomial, the estimated autoregressive polynomial, evaluated at e to the minus 2 pi I omega squared. And this is exactly what we did, again, a couple lectures ago. But now we're doing it with the data. A couple lectures ago, we just didn't have hats everywhere. Now we have hats everywhere, so we're estimating all of the parameters via the data. So basically, we can also get some asymptotic results here, which is nice. So first of all, let's box this off. There we are. Okay, so asymptotically, we have that, our estimator, f hat x omega, divided by, now it's going to change. Remember before we had a chi-squared thing in the denominator. I'll write that again, just so we can see it again. But in this case, what we're going to have is a 1 plus the square root of 2p over n times z, which is going to be our threshold for the normal distribution, our z-score at 1 minus alpha over 2. And this is less than or equal to the spectral density, which is less than or equal to f hat x omega divided by the same thing, but now we're going to, am I getting this? Yes, actually, yeah, what I should do is I should say we have to add not 1 minus alpha. I got it backwards. We want to always figure out which way are we going here. This is going to be a negative number. We want that thing to be smaller. No, I had it right. 1 minus alpha over 2. And then over here, Just making sure I get my subscripts correct. 2p over n, and this is going to be z alpha over 2. So just to make sure we're clear what I mean by those z's in the denominator is that if I had a normal distribution that looks like that, more or less, then I'm going to have 2 points. I'm going to have a z alpha over, or not alpha over 2, a z alpha over 2, which is going to be a negative number such that this area sums up to alpha over 2. And I'm also going to have another point, which is going to be z1 minus alpha over 2, which is the same idea, so that this area here is alpha over 2, or the complement of it is 1 minus alpha over 2. Okay, so now what we have is we have something that converges, and we get something to a normal distribution, slightly different than what we had before. Because what we had before, if I can go find it quickly, yes. So this is, for comparison, before we had that our estimated periodogram, right? We had something like 2 times the non-parametrically estimated periodogram at some parameter. Remember, I had to have that weird little omega j to the t. Here I don't, in the case of parametric estimation, I don't need that because I can evaluate this for any omega. In the case of the non-parametric estimation, we had the periodogram itself coming from the data, and we couldn't just estimate that at any given omega. And there was a chi-squared with 2 degrees of freedom, 1 minus alpha over 2 here, less than or equal to fx omega, less than or equal to 2 times the periodogram, again, at omega t, omega sub j, t, chi-squared 2 alpha over 2. So again, we have 2 different ways of computing a confidence interval for our spectral density at some frequency omega. We can do this via the periodogram estimated non-parametrically, and then with a chi-squared statistic, or what we can do is we can use a parametric model, fit an AR process, and then use the normal distribution. So these are equivalent ways to approach this, and there are pros and cons to each. If our data is really close, well, first of all, if it's coming from an autoregressive process, we probably want to fit an autoregressive process to it. And even if we have an ARMA process, there's a good chance that we can fit an autoregressive process to the ARMA process that's close enough in the sense of a infinite causal linear process that we can still get a really good estimate here. On the other hand, if we have some kind of crazy process, maybe we want to approach it more non-parametrically, but we're going to do some examples. So maybe we'll try to gain some intuition as to which works better when we actually do some examples in R. Now, there is a couple little things to note. So note from the theory, which we are not going to cover, but there's a reference in the that textbook by Shumway and Stouffer, if you want to know more about this, is that note that from the theory, we require, remember this thing up here is asymptotic. Let's get another color there. Now this is, I already said it, asymptotically, right? That's kind of a key word here. So what that means is that the data size t has to go to infinity. Oh, yeah, that's right. I always forgot. I was using t, but the textbook where I was noting these remarks uses n. So we're going to divide by t being our total data size, not n. Anyway, what we require is we require t to go to infinity. but we also require that p cubed over t go to 0. That's a weird looking thing the first time you see it. What it's basically saying is that the order of the autoregressive process has to grow slower or than the data, specifically at like this cubic rate. So that means that we don't want p, the order of the autoregressive process, to go off to infinity too quickly. It can go to infinity, but it can't go to infinity too quickly. And specifically, why would we care about p going to infinity? And the point is that recall that for a causal, making sure I get the right word there, ARMA PQ process, we can write that xt is actually just going to be an infinite causal sum. In this case, I guess we'll take, I forget which index I used to use. We'll just take I think I was using I, from 0 to infinity of psi I wt minus I. I did it backwards. I wanted a invertible. That is very much a true statement, but what I actually wanted, so we're going to keep that, but what I actually wanted was to say, if it's invertible, ARMA PQ. Sorry, it's so easy to get those two backwards. Which one do I want? Well, what I want is if I have an invertible ARMA PQ process, then what we can do is we can write xt equal to wt plus a sum I from 1 to infinity of pi I. I probably should be careful using pi because we actually did use pi up above as the actual number pi, the ratio of the diameter to the, or the circumference to the diameter, whichever way it goes. Regardless, these are the coefficients for our invertible representation. So what I'm trying to get to here is that this is an infinite AR process, but pi I will go to 0 very fast. So ultimately, most of the pi i's are not going to matter when it comes to fitting an AR process, an AR model to ARM a data that's coming from an ARMA process, right? We're fitting an AR model to data from an ARMA process. And technically, if the moving average piece is, I guess, it exists, if Q is greater than or equal to 1, then we'll have, and assuming it's invertible, which we do, then we can write this as an infinite AR process. But typically, those coefficients pi will have, well, they have to go to 0 quickly enough mathematically, and typically they'll go to 0 very fast. As a result, we don't need to have a very large value of p. We don't necessarily have to have a very large value of p in order to estimate a spectral density here. We could just take, p equal to, say, 5 or 10 or something like that. Much as we saw if we tried to use the AR function in R to fit an autoregressive model. But we can make this a little more precise with an actual theorem here before we conclude. All right, so ultimately, this seems like a reasonable approach, right? We can fit a model to our data and just compute the spectral density from that fitted model. But it's always good to have some type of theoretical guarantee rather than just kind of saying, yeah, that kind of makes sense. So what we do get is we get a theorem, which we will not be proving in this course, as we are nearly done here. And I just want to hit some of the most useful bits before we have to wrap it up. So for a stationary process xt. This could be, right. The point is here is that this could be an ARMA process, but it could be something else that's just not ARMA. ARMA or not ARMA or whatever. The point is that this is a very general statement. We're just saying we have a stationary process. Great. Then for any epsilon greater than 0, it's always a good time when you get to have any epsilon greater than 0, we can, or maybe there exists a p. There exists a p greater than or equal to 0, I guess. If we had white noise, it would be 0. So greater than or equal to 0 such that writing such that for, how do I want to write this? Let's try y. For yt equal to the sum, in this case, we'll take k from 1 to p of phi k y t minus k plus wt. So this is just an ARP process. I guess I should say this also exists. So there exists a P, maybe not such that, and so make sure my English is correct. For any epsilon greater than 0, there exists a P greater than or equal to 0, and there exists a YT, which is an autoregressive process of order P, such that the difference between the spectral density of X for our general whatever stationary process and the spectral density of Y, our specifically our autoregressive process of order P, is going to be less than epsilon, and this is for all omega in minus 1/2. That for all is actually quite nice, right? Because it means it holds uniformly for all omega. But I guess on one hand, yeah, you could probably, there could be ways to strengthen this, I guess, but I'm not gonna, I could ramble on and think about this, but we're not gonna do that now. And then the other thing is we have this where P is finite and YT is causal. So it's nice in that sense. So what does this theorem say? Well, it basically says in words, that is, for any stationary xt, we can find an ARP process with spectral density really close in the sense of epsilon, really close to the, we'll just say spectral density of, wait, which one are we doing? We can find an AR process with a spectral density really close to the spectral density of xt. So that's kind of neat, right? It's it almost feels like a density type argument, right? Where it's like how polynomials are dense in the sense of you can approximate continuous functions via polynomials. In this case, it feels a lot the same way. where you're saying that, okay, I have a stationary process. It's going to give me whatever crazy spectral density I could imagine. And there's going to be an AR process that's really, really close to it. So let's fit an AR process to our data and use that as an estimator, a representation of the spectral density for our process. How does this all work? Well, we're going to find out, but we're going to have to jump into RStudio to do that. So I will see you in a minute and we'll come back in RStudio. And welcome back. And now we're in RStudio, where the first thing I've already done is loaded in a whole bunch of time series libraries, TSA, T-Series, Forecast, and the ASTSA, ASTSA library, just so we have plenty of them to work with. Because I always forget which functions lie in which library, or package, I guess I should say. Technically, they're called packages, yet you use library function to load in the package, so I always find that terminology kind of strange. Anyway, I've also set a random seed here to 479. I sometimes forget to do that. My apologies. This time I remembered. So you can follow along at home if you'd really like to. Anyway, what we need is we need some data to work with. So before we look at any real data, what I want to do is just simulate some autoregressive, some moving average data and see what we get. So the first thing we'll do is we will use arima.sim as we have done in the past. And we're going to fit a model that is going to be an AR1 model. And I'll pick my coefficient of 0.8 because I like to have a large enough autoregressive coefficient that I can kind of see what's happening here. And we'll pick 500 data points because, why not? You know. While we're at it, maybe we can do a seasonal one, an AR4, where I'm just going to put 0, 0, 0 in here. So this would be like a seasonal AR1 model with a period of 4, if that makes sense, right? While we're at it, we could do the same thing for MA, just to create a nice set of data for us to work with. So I can just change this to MA. I'm going to try to keep it as simple as possible. And lastly, we can do the same thing with a 4 here and say 0, 0, 0, 0.8. So that should give us enough data to start with. Just because I always like to look at the data before I start, let's look at the data and see what we get. So what I can do here is just say plot AR1, and it looks like that. Plot AR4, and it looks like, well, that. Plot MA1 and plot MA4. So yeah, plotting time series, not always the most interesting thing. They all look really noisy, as I guess a stationary process is, expected to do. Anyway, now we can do things that are a little bit more interesting. First, I'm going to reset my plot here so I don't end up with a whole bunch of little plots, but one big plot to look at. So in R, you can find a lot of different functions, but one of them, I guess the main one we're going to look at, is called spectrum. Now notice that there's actually a spec.ar, a spec.pgram, so autoregressive, periodogram. This is parametric, non-parametric. There's a spec.taper if we want to do tapering, much like we talked about in the last lecture when we applied specifically that we wrote down that the functional form for that cosine Bell taper. In this case, that's what that function spec.taper does. The TSA library also has a spec function, which kind of does the same thing as, I guess, spectrum, which wraps the AR and the pgram into the same function. So let's just look at that to see what it's doing. So this one, in some sense, documentation is really not that interesting. It basically says, estimate the spectral density, and we can either do it non-parametrically via the periodogram, or we can do it parametrically via estimating an AR model first. And otherwise, there's not much going on here. So it can tell us more if we look at these two specific functions. Let's look at the AR first. So here, spec.ar is going to estimate a spectral density by fitting an autoregressive process, just like we just talked about in the written notes. And there's not too much else going on here. You can select a specific order if you want, but otherwise it's going to use AIC to choose. And like I said, it's always good to double check how these functions work, because they could use AIC, they could use BIC. It all depends on who coded it up and what their favorite method is. In this case, it uses AIC, which is good. It means it coincides with just the regular AR function, which is, I think, precisely what it's using to fit this. So that means, assuming all the defaults, I'm guessing that it's going to use the Yule-Walker equations to estimate the autoregressive parameters. Otherwise, there's really not much else here except, some authors, for example, this guy, Thompson, well, I guess Thompson's a last name, so this person, Thompson, warns strongly that AR spectra can be misleading. That looks troublesome. On the other hand, if you read the textbook by Shumway and Stouffer, they say that oftentimes different types of researchers will prefer to use this approach, especially because it can get a lot of little tight fluctuations in the spectral density that would be hard to catch in the data. Because if you try to fit a spectral density non-parametrically and you smooth it out, you can get those big trends with smoothing, but you're going to miss that little fine detail. So I've heard both cases. I haven't actually read what DJ Thompson has written in the 90s about this. So, hey, but there's a link. So I guess if you really want, you can go check that out and see why that author may or may not be a fan of the AR approach. Anyway, there's also the p-gram. Statistics really does have an art to it, right? It's like there's always 100 different methods to do the exact same thing, and you always have to wonder, well, what's the right one? Or which one should I use? And there's really never a good answer. So try them all and get some intuition about what's happening with your data. Regardless, if we want to do the non-parametric approach, we can use a smoothed periodogram. So by default, this will not do any smoothing, but it will use the modified Daniel smoother, or the modified Daniel kernel, to do the smoothing. I think there are ways in here to actually even modify the kernel more, but in this case, if you use the spans argument, what you can do is you can set a type of Daniel kernel to work with. This also has the ability to do tapering if we want to apply a taper to our data before proceed. I think by default it does a 0.1 there. Regardless, there's not too much in the details. Okay, the raw periodogram is not a consistent estimator of the spectral density, but adjacent values are asymptotically independent. So the point is, a consistent estimator can be derived by smoothing the raw periodogram. So in this case, it's basically saying, yeah, you probably want to smooth. Another interesting thing here is, remember, when we estimate the periodogram directly, what we're doing, right, is we are using a Fourier transform. So in this case, what it does is it actually pads some zeros onto my data to get a power of 2 in order to get a really fast Fourier transform. So in this case, since I generated 500 data points, it'll actually pad on 12 zeros, so it can do an FFT. Now, we didn't talk about this in the written notes, but there are ways to adjust some of the coefficients if you pad zeros onto your estimate. Typically, you would have to subtract or add to make sure that the amount of data, real data you have, is there and you're not using the padded version, right? Because if I add on a bunch of zeros, I'm not creating new data, so I need to make sure that I still use t, or in this case n, or whatever is equal to 500 in the equations, but R will take care of that for you. All right, well, that was a lot of rambling about all these functions. Maybe we should actually try them and see what happens. Let's start with spec.pgram. We can do this actually via Spectrum itself, so maybe I'll do it that way so that we can see how it works. In this case, I can give it my AR1 data and the method, which in this case we'll say is, I think, pgram. And what do we get? We get something that looks kind of, well, crazy noisy. Yeah, it's not the cleanest thing. One thing to note, this is on the log scale. So if you notice the vertical axis is actually decreasing in the number of decimal places, right? We have like 50, 5, 0.5, 0.05, and so on. It's always good to know that in this case, it's plotting as a log periodogram. That's often the default. There is, just to keep on my random walk here through RStudio, in the TSA library, there is a periodogram function. This one will default to plotting the periodogram as a on the absolute scale. So if I do this, you're going to see a bunch of what the periodogram would look like, but on an absolute scale, not on a log scale. So it does change it a little bit. So it's always good to know what you're plotting and what the axes are doing. But for now, I'm going to jump back to this plot, because right away, it doesn't look so great. It's kind of noisy. It looks like it's roughly decreasing. So maybe we should try to smooth it out. And what we can do is we can use span. And what spans, sorry, with an S. And this is going to apply our modified Daniel kernel to the periodogram. So I can pick some odd numbers here, which is, I have to double check what the parameter is, but it's going to be like the window, the width of the kernel, and I think the number of times that you apply it to itself to make it like a smoother thing. Regardless, if we do that, we get something that looks smoother. Now I could actually increase this a lot to like 31, and we get something that looks a lot smoother. So again, the more you smooth, the nicer representation you have of the big trends in the periodogram here, but we lose a lot of the little details. So if there are little local peaks or fluctuations, over smoothing will destroy those. And what we see is a big trend, which is start high, go down. All right. But again, we will lose any sort of local interesting features if we over smooth like this. In contrast, if we were to just do the AR process or fit an AR process, we get, well, yeah, a really smooth representation. In this case, interestingly enough, it seemed to fit an AR2 model to the data. I think it just uses the AR function, so we can see what it gives us. Yeah, it did actually give us a second coefficient incorrectly, but that second coefficient is really small, so it probably doesn't have a huge effect on estimating things like the spectral density. And notice that it also computed the variance here, which is slightly lower at 0.9 than our 1, but it's not that much lower, so we're still good. Anyway, this is the smooth, or this is not the smooth, this is the parametric version of the periodogram, and this is our smoothed non-parametric. This is our much less smooth non-parametric and our, well, original one. Now, interestingly enough, I think what we should be able to do is save this as spec.ar, spar. And then what I want to do is go back to the raw periodogram to see how well it fits it. That is, how well, if I plot the two on top of each other using the lines function, spec.ar, spec, and then we'll just say color is red. And yeah, there's what we have. So what you have here is the periodogram for the AR, estimated AR function in red. Now, or the spectral density, sorry. Periodogram, I'm getting the terminology backwards. Periodogram is strictly coming from the DFT of the data. The red line is an estimated spectral density based on the estimated AR coefficients, or the AR model here. In some sense, the red line is kind of the right answer because the data is an AR process. But we don't know that. I mean, we know that in this case because I generated the data that way, but a priori we wouldn't know that. But you can see here how you get a very extremely smooth kind of version of this noisy periodogram. It looks like here I accidentally plotted it over the smoothed periodogram with like a weak smooth with a 3-3. If I plot the same thing over the this periodogram, the two should presumably line up pretty close. Yeah. So you can see that here the two spectral density estimators line up very closely to each other when we over smooth using the modified Daniel kernel. There's like a ton of terminology here, so I gotta make sure I get this all right. And that my voice holds out until the end of the lecture. Anyway, I want to look at what would happen if we do this to the other functions, the other data sets that I generated. But first, I want to look at the kernel. So it doesn't really tell us what it's doing with respect to the modified Daniel kernel, but luckily R is open source. So if I just type this in, I can get the horrendous source code. No offense to the coder. It's actually, I mean, probably really well done, but any source code looks kind of nasty when you just plot it out like this without any syntax highlighting or otherwise. Anyway, you can see in the source code where like the FFT is computed. You can see other things. But specifically, somewhere up here, we have a command that says, well, if spans is not null, then use the function modified Daniel kernel on it. So let's see what that does. So if I apply this now, I think this this percent/% is dividing by 2, but I guess removing the remainder or something, but I can double check that to see exactly what it's doing. Anyway, we can use the kernel function, tell it we want modified Daniel, which is what is hard coded into this. So presumably you could use the, there's a TS kernel argument somewhere hiding in here. I forget where it is. So you might be able to, if we really wanted to, figure out how to specify your own kernel, but honestly, they all kind of do the same thing. They smooth out the process. So might as well just stick with modified Daniel right now. Anyway, if we look at this, it's going to spit out some coefficients at us, which while we stare at it might not mean a lot. But if we were to plot the coefficients that it spit out at us, then what we would get is something, let's say type is equal to B. We get something that looks like that. So it's almost a triangle in this. It's almost like a linear up and a linear down, but just not quite. On the other hand, if I did that 31-31, I'm going to get, well, something that is just like a triangle, but there is a noticeable difference here. Here, the window is stretching from -30 to +30, whereas over here, it's just stretching from -2 to +2. So there is a big difference there. That's interesting. Maybe that's a 1-1, whatever, it doesn't matter. What's interesting to note here is that they're both filtering or smoothing, I should say, with something that looks kind of triangular, but this one is a much wider window. So it's spanning over about 60 different frequencies, whereas the other one, when I use 3-3, is only spanning over like 5 frequencies here. So that's what really makes the difference. Now, if I just start like, haphazardly changing the values here, like if I change this to 15, now we have something that looks linear, but with a flat top here. So it's kind of saying that all of these middle frequencies get evenly weighted, and then we taper on the edges. So again, all of these little dots are the coefficients that correspond to the weights for a weighted average. If it's just a big flat line, then I'm saying equally average them all equally. If it's sort of a linear line like this, then it's saying that for every point closer to the center, give it a higher weight. In contrast, if I switch this to 15 and 13, I think I should get something polynomial-like. Maybe not. Oh, I got the same thing. Interesting. Maybe my intuition is off with respect to what these parameters actually mean. Oh well, no worries. I think we can actually play around with this a little bit more just to get some idea. Yeah, if we take it to one extreme, we get something that's going to look like just a big average. In this case, it's like we're just averaging all the data points equally. So again, you can play around with this just to get a sense of what's actually happening in practice. You know, there we go. I got something that looks maybe slightly more quadratic in the sense that it's kind of rounded at the top rather than just like a flat top. So, okay, there's, as I said, you can do this forever, but effectively it just shows you an idea of what these kernels look like when I change the span parameter in this function call. All right. Well, now that we've done that, let's go back and plot some more spectral densities, because we can do this for an AR4 process. That is our seasonal model. And oh, we get something that looks quite different now. We get this kind of little W shape almost with this spike right in the center, which is quite interesting. In this case, it got the right answer, which is that we need an AR4 process. And just to look to see what the coefficients are at fit, you can see that we have very small values for the first three, and then a big one for the fourth one. So it's not fitting a seasonal model, but it's getting pretty close to it by noting that these coefficients are all small. The last coefficient, it's big. If instead we were to use the periodogram without smoothing, yeah, it's a lot harder to notice that because you have these really big spikes like here that kind of obscure what's going on. Now, in contrast, though, if we were to smooth it, not spans, let's try that 7 and 9 one. That seemed like a nice smoother. Like, that's not so bad, right? It still captures a little bit of noisy stuff going on over here, but you can roughly see the trend, and you have to remember that this is on the log scale, so this peak is a lot more significant than any of these other little peaks in here. Again, log scale. I guess if we were to actually just use periodogram, we would see this much more blatantly, right? If we don't do it on the log scale, we just see our 3 spikes here pretty clearly. Yeah, roughly. I don't think there's much else you really want to do here. We could just have like a stupidly over-smoothed version. That's probably overkill. You get that W shape, but it definitely doesn't look like what we wanted, right? This shape looks a lot different than the AR one that we had before. So over-smoothing, bad. Under-smoothing, bad. How do you smooth exactly? Well, you have to just kind of take a good guess. Okay, but what happens if we do the MA process? Because the MA process is not an AR process. If we try to fit an AR model to an MA dataset, we get something that looks infinite. Well, not infinite, but it looks like a high order process. And oftentimes you see flipping signs in your coefficients here. Okay, so what's that spectrum going to look like? It's going to look like that. Right, and here's where, yeah, you have to be careful with kind of noting some of these weird little bumps, right? Because if you were to over smooth this, you would lose those. Again, without smoothing, it looks really terrible. You can't really get a lot of good information out of that. On the other hand, not spans. If we were to smooth, okay, we get a lot of little humps. It's not really obvious what's going on here, I think. We can try, say, a more aggressive type smoothing, just kind of play around with these parameters. you can get the rough overall trend, right? That it seems to start up high and drop down. But what we do miss is we miss some of those little humps, right? That you would see in this case. I mean, I guess we kind of noticed that there's another little hump over there at the end here. It's kind of popping up here a little bit, but it is a little bit harder to notice these. And it's one of the reasons why I think people like using the parametric approach. Again, assuming that the parametric model is the AR process is a good enough fit for your data. And lastly, before we end this section, we're going to do a seasonal auto or moving average process, which, yeah, if we try to fit that, we're going to get something crazy like an AR16 model, right? Because notice that these first three coefficients are completely like negligible. Then we get a big one, then we get some small ones, and then it's just like 12 is kind of big. 8, I think, fell off the kind of fell off the page here. 8 and 9. So much for oh no, there's 8 and 9. Wow, that's terrible the way it kind of it did that. But regardless, right, we have a lot of it's not quite clear what's going to happen here. So let's try to fit that once again. We'll do it with the p-gram first. If we unsmooth it, well, we get that. At least there we can kind of see some pattern that it's kind of, well, up, down, up, down, up. But maybe if we smooth it, we can get a better sense of what is happening here. All right, so there's the up, down, up thing happening. But we can also use, of course, the AR method. And we capture it a little bit more closely. And you do see a lot of very peculiar little humps here, up and down. So it's not the it's not just a nice smooth curve like we saw before. And remember what these correspond to. This corresponds to the intensity of different frequencies in our time series. So there are points where the frequency doesn't like certain frequencies that don't exist at all. And there are other frequencies that come in very strongly. And remember, if we were looking at white noise, it would just be a flat line all the way across. I mean, a noisy flat line, but ultimately just a flat line all the way across, which would tell us that all frequencies are represented equally. Here, there are definitely some differences that we would have to take into account. All right, so there's one other question about our theoretical or our simulated data, I should say, our simulated data that we might want to ask, which is, what does the actual spectral density look like the true spectral density? Well, since we have an ARMA process, we can use the ARMA spec function from the TSA library or package, that is, to actually compute this precisely. Now, that's not to be confused with lowercase arma.spec from the ASTSA library or package, which does tests for causality and invertibility based on the spectral density. So once again, there's lots of time series packages. They all kind of do the same thing, and they will have functions that are named almost identically to each other. I think they're all associated with different textbooks because, yeah, everyone who writes a textbook figures put out an R package, which is a great thing, except when they all have the exact same functions that are all slightly different or do different things with the same names. That's my quick little rant. Anyway, what I want to do is say par mf column C 2 rows 1. So what we're going to do is we are going to say ARMA spec, and then for our model, oh, I need a list. For our model, what we're going to do is say AR is just going to be 0.8. And what do we get? Well, we get something that looks like that. And what did we get when we fit a spectrum, fit the spectral density using the AR method? Well, we got something that looks like that. So yeah, it's not so bad, right? The actual answer kind of tapers off more quickly, Probably because maybe it's because we fit an AR2 model here rather than an AR1. Ooh, in fact, we can do that. Let's try it again. So if we replot that first plot, but we come in here and we use spec.ar and tell it that the order I want is 1. Nope, it still gave me something kind of spread out. So I'm just making sure it's the same axes. Yep, no, it looks good. Yeah, so regardless, we get something here that's a little bit more spread out in the way that it thinks the frequencies behave versus the true answer, which is a little bit more concentrated, but all right, close enough, I guess. Now, what would happen if we did that seasonal model? Well, the seasonal model is going to look something like this. And the one that we fit to our data is going to look like that. So again, we still got the same, roughly the same idea. Oh no, it's not on the log scale. See, that's what I was thinking. That's the problem. It's the top one is not on the log scale. Notice that it goes 5, 10, 15, 20 versus here it goes 0.5, 5, 50. So there's the difference. I had a feeling something like that was going to happen. Let's see if we can just say, nope, it's going to get mad at me if I do that. All right, so maybe we're stuck not being able to plot this on the log axis, which is a little annoying. Yeah, I don't see any strict way to, I guess I could probably export it and then plot it a second time, but whatever. Maybe we can plot the other one on a non-log axis. We'll just double check the, all right, well, we're just going to have to imagine in our heads what's going on because these functions don't seem to play nicely with each other. They are from different packages, so it goes. Anyway, yeah, let's go back to here. I guess I rescind my previous comment. Now, what in the world is it doing there? R is just yelling at me now. Whatever. We still got the picture that I wanted. And if we plot this, we get roughly the same thing on the log scale. So I rescinded my previous comment about the AR1. I think that the two fitted things look almost identical to each other. Oh, in fact, I have a better way to do this. Sorry that I am more or less just kind of working extemporaneously here. But we can actually plot these on top of each other. And then it's going to look much better. So there is my crazy, yeah, I think this should work. Let's see if it works. That's the, this is the spectral density for the exact spectral density for a seasonal AR process with a period of 4. Now, if I call this out, that's going to plot it for me, of course. And then I say lines out frequency, out spectrum, and color is red. Let's see if it gives it to me. Yep, there we go. So here is actually quite nice because you can see, probably would have been better to plot these on the log scale, but whatever. You can see that it, it does miss the intensity of this peak here, but it still does a pretty good job at kind of climbing up here in the middle. And it gets roughly the main shape, which is some of the main points. What happens if we do this for an MA? So if I were to change this to MA and delete all of this, we get something that, again, looks quite smooth there. But if you recall what happens when I fit my MA1 data, I get something kind of bumpy, right? So in some sense, I guess over-smoothing a non-parametric estimator is perhaps a better way to represent this than using the AR way of fitting it. But let's plot them on top of each other. Yeah, look at that. So you can get a sense here that using the AR method for estimating the spectral density here is not doing as well as we would like, right? The true answer is going to be this black line, whereas from our data, we got this crazy red line. Now, what would happen if, in contrast, we were to fit this using the p-gram method and we were to smooth it? Maybe not over smooth it. Let's try a sensible smoothing, like 7.9, which is the one I was using before. Well, if we do that and we go back to our this plot, then we can plot blue. Hope that no one out there is red-blue colorblind. I apologize if you are. And actually, yeah, it still looks pretty terrible. So, right, it's yeah, not great in some sense. We'll try and do one over-smoothed version just to see what happens. Now that looks more like the right answer. But of course, you always have to be a little careful, because if you over-smooth, you don't know a priori that all of these humps shouldn't actually be there. So working with real data is kind of a pain. Where did my plot go? There's my plot. Let's call this green and then just make the colors terrible, and we'll do LWD is equal to 3, so it's easier to... Oh, now it's just mad at me. Oh, because Gren is not a color, but green is a color. All right, so there's my over-smoothed. This is actually quite interesting, because notice how it kind of underestimates at the beginning and overestimates at the end. That could be an artifact of the smoothing, because... Okay, just in general, when you're smoothing something in statistics, you're typically reducing the variance, adding in some bias. So the fact that I over-smoothed this to some absurd extreme, and it gave me something that looks like a very low variance estimator, but something that certainly has some kind of bias as we move throughout the frequencies here. So that seems to be hinting at what's going on here, that we've kind of gone a little bit too far with the bias variance trade-off, but at least you get a kind of a smooth representation of what you think should be happening. Anyway, that plot looks horrible, so let's try to make another one. And the last one that I want to do, if I can find my ARMA spec, is to look at what a seasonal MA model, the spectral density for a seasonal MA model with a period of 4 would look like. And oh, we got a little sort of wave up and down. We still have that W shape, a little bit different than the one for the AR model. Yeah, so let's see what happens when we try to fit that, let's see, that spectral density to it. And we don't want this, and we want to just switch back to AR. And yeah, remember last time we ended up with these random humps. And again, a priori, we don't know if these humps are supposed to be there or not. We can certainly smooth them out, but especially like when you see this, you might think to yourself, well, are these little humps actually features of my data or just the estimation method? So once again, if I go back to that true plot, what I can do is I can just plot right on top of it with red. And yeah, it's capturing what's going on, but we do have some weird little fluctuations here that are not present in the actual spectral density. And just for the sake of completeness, we can do the same little trick looking at where is it? Here it is, the smooth version. So if I set this to 4, and maybe let's increase this a little bit, but nothing too crazy. Okay, so that's, well, not exactly the right answer, but it might be a little bit better. Let's plot it over top of what we had before and see how well it does with respect to the black and the red lines. Where is my lines? There it is. Cool. So that blue line actually isn't too terrible. It's still not, it still has this interesting feature at the beginning where it kind of starts down and goes up rather than just decreasing. And similarly, I think over here it's a little bit messier, but yeah, so there's a whole bunch of examples of how you can estimate spectral densities in R. So what's the takeaway here? Like, what do we gain from trying all this out? Well, what I think we notice is a couple things. If your data is actually coming from an autoregressive model, then using spec.ar is probably the right way to do it because it's just going to capture it really well. Now, theoretically, if the data size gets really, really, really big, we should be able to use spec.ar to fit a really good model to get a spectral density out that is really close to the true spectral density of the data generating process. In practice, we see that even with an MA1 or an MA4, you do get some mess in there, and that perhaps using the non-parametric estimator and smoothing it out would be better. Now, when we smooth things, there's a bias variance trade-off. If we don't smooth, it's going to look really terrible, as we saw. If we smooth too much, you might lose some of the interesting local features. You also just might under or overestimate at different parts because of the fact that there's now bias in your estimate. So yeah, there's a lot of different, like, it's a pain, basically. That's what I'm trying to say. It's kind of a pain to figure out what you want to do when you're estimating a spectral density. You have a lot of tools at your disposal, and ultimately you're just going to have to try different tools applied to your data set. Try undersmoothing, oversmoothing, parametric, non-parametric, anything else you want to get an idea, right, about what's going on with your data. Because ultimately that's what we want. We want some intuition about what's happening with our time series data. And when you see things like humps like this, you can start to get the sense that there might be some periodicity, that is some seasonality in the model. If it's flat, it's going to look like white noise. If the spectral density vanishes, then those, or goes really small, then those frequencies are not represented in the data. Right? There's a lot you can learn by staring at these spectral densities. And the only way to get it is, well, to just stare at them a lot. All right, so that more or less wraps up everything I wanted to talk about with respect to spectral methods for time series. But luckily, we actually still have 2 lectures to go, so we can get some more bonus material in before this course is over. And we'll talk about that and the new topics in the next lecture. So I hope to see you there, and yeah, have a good one.